So KitchenSink is a tool that you can use to interact with remote data and remote computation as if it were local, but we have actually two things for that. The second is going to be a mix of using Bokeh and Blaze, which are open source products by Continuum, and something that we're thinking about releasing into the closed source product pipeline called the Anaconda Data Portal. But we're going to start off with KitchenSink. So the initial motivation, why I wanted to write KitchenSink is because I was doing some consulting work on client sites, and I was building HTTP or web-based data access endpoints on remote machines, which needed to be hit by JavaScript web clients. So people had to build JavaScript web applications that would talk to these remote machines. But also Python users had to talk to the same functions and get data back. The first problem was that I got really tired of writing out web boilerplate code every time I wanted to expose new functionality. So has anyone here ever written web applications? Okay. Who likes writing web applications? Okay, so there weren't that many hands to begin with, but it went down a little bit. I do not like writing web applications, even though that's what I spend the majority of my time doing these days. So anything that sort of eliminates writing, like I don't want to write the web code. I just want to write the function and have that automatically be called. So that was the first motivation. The second motivation was that when you're deploying a web application in production, you have to worry about things like timeouts, and then suddenly if the user is calling a function that takes a long time to run, maybe it's killed by your timeout system. In this case, we were using GUnicorn, and it got killed by the timeout, and diagnosing these problems was really cumbersome. And the final motivation was that people who are interacting with remote data sources, they would issue some computation from Python. Maybe the functions, the variables that they passed into the function were incorrect, or maybe there was something wrong with our system, but there'd be an error. And so they would get a message back that there has been an error, but they wouldn't know why, right? So has anyone worked on distributed systems before, or working with stuff on different machines? Okay, so a lot of people. And so when there's a problem, what do you usually do? Andy, what do you usually do? Okay. So most people can't do that, I think, because it's not necessarily easy to connect to a grid and debug. What I usually do, so this is the answer I expected, was most people will go to that machine and look at a log file, and it's really cumbersome, and you search for the stack trace, and you find the stack trace, and you debug it, right? But anyways, being able to have analysts who aren't Python experts be able to do computation on remote machines and get stack traces back is really useful. That was originally why I started working down this route. And then the follow-up motivation is that, well, it's also nice to parallelize computation, right? Generally, parallelizing compute is very cumbersome because I think that most of the solutions out there, like Disco and Hadoop, are centered around writing MapReduce jobs. I personally feel like, and maybe you guys will disagree, that writing MapReduce jobs is cumbersome because oftentimes you just have a function and you want to apply it to a data, and map does that, but you don't want to deal with reducing and other stuff. IPython Parallel is a great solution for this. If anyone has not used IPython Parallel, you should check it out. It's very convenient. But I am hesitant on using it for batch jobs and production batch jobs because the subsequent execution is dependent on the state of the current running kernel. And for a production system, you may not have that much control over that. Like as you're building up computations, the kernel state might be modified, and then who knows what's going to happen. So I would like to have a solution where these like big data capabilities of Disco and Hadoop are combined with the interactive ease of IPython. And so I thought, what would happen if Disco and IPython Parallel had a baby? And I tried to synthesize that into KitchenSink. So the initial feature set is to, yes? I'm sorry, can you, no, it's a good solution for that. I think for production batch jobs, I'm a bit wary of it because each subsequent function that you execute depends on the kernel state that, like the kernel's a live kernel. And as you execute subsequent functions, you may be modifying that kernel state. And so if jobs are scheduled differently or like, I like to keep the state around a function fairly, yes. But for interactive work, I think IPython Parallel is great. So the initial feature set is to make it feel like you're working locally when you're really working remotely. And what we do for that is passing back standard out to the client and passing back errors to the client. This isn't as good as allowing remote debugging, but allowing remote debugging is tricky. I think this gets you 90% of the way there. The other thing to support large data sets is to support server-side data and to support fast formats. Like HDF5 and B calls are very fast data formats. I want to support any data format that you want. And then to take advantage of server-side data, you need to have some sort of data locality-based task routing. And then the other thing is that in order to, in order to support letting web applications talk to it, you need to support multiple serialization formats, right? Because if everything that you're doing is in pickle, then your JavaScript client can't talk to the thing that you built. Okay, so live demo. So I have 2 KitchenSink servers running on my laptop. So this is, I'm going to pretend like it's a remote data, but really it's local. But I am talking to it as if it were remote, so if it was running somewhere else, that would be fine. Here's to just initialize the client state to point to that web address. And so this is sort of the hello world. I'm just going to add 2 numbers and call it via KitchenSink. When I do that, I get 3. So here, CS is just a shortcut that I wrote for a call single. It calls a single function and returns a result. Most of the functions in KitchenSink are organized around executing many functions, because when you're doing parallel computation, typically that's what you're doing. Here's a map function, right? It's similar to the map that you would expect. It doubles everything and returns the result, but all the computation is being done on a KitchenSink worker somewhere. The workflow that I typically use in my usual computation is I use bulk call for a bulk call that sort of queues up the job. So every time you execute BC, nothing actually happens besides the client records, I want to execute this function. When you call execute, the function is sent to the cluster and computed. When you call BR for bulk results, you pull the results back. So if I add 1 and 2, and I execute that a bunch of times, I get back a list of 3s. So that, nothing is really interesting about that. It's just boring functions being evaluated. I think the more interesting stuff is dealing with passing back standard out. So I'm going to execute this function, and you can see that it's printing back the intermediate results, right? This sort of is a dummy function that simulates what a lot of people write in long-running tasks, where it's you're doing a long computation and you say, okay, I've finished this step, I finished this step, I finished this step, and you have these steps in a log file. This streams it back to you so that you can see it interactively. You can turn it off, that functionality, but it's convenient to have on by default. And then this is going to show you that if we, so what I was talking about error handling, right? So I'm going to call the add function on a string and a number. That should produce an error. And so you can see that I get the stack trace back from the code that was executing on the server. But as I mentioned, we're trying to do some parallel computation. And so here I wrote a dummy function that we know sleeps for 1 second. And I'm also printing out the machine that it's running, or the configuration of the machine that it's running on. So I'm just going to execute this in the IPython kernel, right? And it's going to take 2 seconds, right? Because I have 2 calls to a function that sleeps for 1 second, okay? I can parallelize this, and it should run for 1 second, right? So these tasks are indeed being executed in a parallel manner. So common issues that you often have to deal with parallelizing computation is that serialization and deserialization become a headache. As your data sets become large, if you're using something, who's used multiprocessing to speed up computations? Okay, so the first thing that people run into when they're using multiprocessing is that you have all these pickling problems. So that's usually solvable. It's annoying, but it's solvable. The second issue that you run into is that serializing the data to pass it to your functions, that becomes the overhead. And so we want to avoid lots of serialization and deserialization. And also, profiling things that are happening on many different places is tricky. So I have a halfway solution. I don't think anyone has like a great solution for that, but this is the best that I could do. So one is just allowing people to store data in HDF5 and bcalls and things like that, which are transparent, because then you can just read the data off of disk, and that prevents you from having to send that data out. And reading data off of things like HDF5 is generally quite fast. The second thing is that in order to prevent you from having to copy data, we want to move the compute to where the data is, right? That's why we take the function, we send it to a remote machine, execute it, and get the result back. And the final part is we have some basic stuff around distributed profiling. To accomplish this, we have remote data objects. They're basically these pointers that point to objects that live on a server somewhere. It's basically a URL that represents a path on another machine. And you can from that object, you can either pull out a Python object, that is, if the underlying data in that file represented a pickled or some other serialized Python object, or if it's a raw file, then you can call local path, and that will return to you a local path to that data. So if the data is on another machine, it'll copy the data and give you a local path. If it's on that machine, it'll just give you the local path where that data is. And then you can also get the raw byte stream of that underlying data. So I have a so here, if I call c.host, I get the list of hosts that I have. You'll see that those URLs are displayed twice. That's because the first is the name and the second is the URL. In the default case, you name the name the same as the URL, so that's why it's repeated. But you can name machines different things. And then I'm going to sort of populate some dummy data. So I'm creating two pandas data frames. I'm calling this reduce tree operation, which is probably not nicely named, but just the point is it takes everything that matches star and it reduces it so that the number of hosts that it lives on is 0, right? Because when you're dealing with a data storage mechanism where data can be replicated, it's no longer as simple as just deleting. I mean, you can delete, but you can also like reduce it so it lives on 1 host or 2 hosts or 3 hosts. And then what I'm doing is I'm saving the different pieces of data on different machines. So I'm saving dummy 1 on the one running on 6323 and the other one running on 6234. And I can do a query for the data that I have in my cluster, which is just those 2 things that I registered. And I can query it to get some information. So the first thing that I get back here, those are the active hosts that I have running. So if a host goes down, then it won't show up on this thing. And then the other is just metadata about where each piece of data lives and some information about it, right? The format that it's being stored in, the size of it, the fact that it's ready for computation, that it's fully copied, et cetera. So this function is calcsum, and I have this little time this context manager that I ripped off from Dave Beasley. And it basically times the thing that's happening inside it. Now, part of the annoyance that I have with these remote data pointers, and we can change this later, but basically, you're passing in this object, which is not really a data frame, but it represents a data frame living somewhere. So when you actually pass it in, you have to pull the data frame out of it. You have to dereference the original data frame out. So that's what this operation is. And then I'm going to print some information about where it's running and what the data URL is so that we can verify that it is indeed being locally routed. And that's the function. Well, the last step is to actually compute the sum. So these are the results right there, the sum of the 2 different columns, and then I'm evaluating 6323, dummy 1 on that one and dummy 2 on 6234, which is consistent with where I stored it. I can also turn off data routing, and if I execute this enough times, so if I turn off data routing, you can see that now it's being executed on the machine that the data is not, and the 2 machines are copying data from each other. The final thing that I want to show you is that we have some basic infrastructure around profiling. And so if I call bulk results with a profile keyword, I can retrieve some profile information, which it basically dumps a lot of numbers, and some of them are not that important, but basically, so every time you have the time this decorator, so I had a time this decorator around extracting df and sum. And so the runtimes for those decorators across all your functions are summed and aggregated into these 2 numbers so that you can see how long each step runs in aggregate across your entire cluster. I also have some information about how long the job took in aggregate, and then I have some diagnostic information. So like the start spread is the time delay between when your first task started and your last task started. In this case, it's very small because the cluster is completely empty. And the ending spread is the time delay between when your first task ended and your last task ended. And there's some other things for overhead. So the summary is that currently KitchenSink, I believe, is ready for people to use. I have been using it personally on personal projects and on some other things that I've done for but we are looking for contributors and looking for users. And when I say we, I mean I am looking for contributors and users. Because it's basically ready, it's a useful tool. I think so. And to show you something that this is a thing, let's see if it will load with the network. I may have to restart some SSH tunnels. Okay, so this is a bokeh thing. So everyone's here has heard of bokeh? No? Okay, well, bokeh is a plotting library that we developed at Continuum. It allows for nifty things like this. This is a 90 million row data set of taxi cabs in New York City. And so what we're doing here is that we are taking the the pickup data, there's information about who, every trip has a pickup latitude and longitude and a drop-off latitude and longitude. And we take that information and we tile that into a 2D grid, and then we send that grid over, right? That way, you can take 90 million rows of floats, and you can send back this like 330 by 550 grid of pixels, which massively reduces the data volume. And then you can sort of change the shading so that it's nice to look at. And then we have histograms of trip distance and trip time. So if I filter by 12 a.m. to 4 a.m., what's happening right now is that the backend that's actually doing the computation across the 90 million rows and doing this aggregation is I have a KitchenSink sitting on a machine in Austin, Texas, doing this computation and then sending me back the data. And then I can do stuff. So what I did was I filtered to 12 a.m. and 4 a.m. So from 12 a.m. 4 a.m. on the bottom I have these comparison plots which compare the densities, the percentiles of the filtered data versus the unfiltered data, right? So the red regions are where between 12 a.m. and 4 a.m. there are more occurrences of this thing than during the normal time period. And so you can see like, this is where people go to party because that's where they leave between 12 and 4 and then they get dropped off in those places, right? And then you can do stuff like, well, I want to see the people that are traveling farther, so I can do that. So I selected longer trip distances and you can see that more, so I mean, makes sense, right? If people are partying here and they're traveling farther, then they're getting dropped off in those outer regions. Does anyone have questions about that? Yes. To do parallel processing? I mean, you just take a like, I would use multiprocessing.pool and then pool.map, and then I would send stuff to the pool.map and get the results back. Yeah. Okay, so now I want to talk about the second thing that I mentioned, which is at Continuum we were building this thing called the data portal, and it is it's technology around Blaze and Bokeh that allows you to interact with remote data sets and do visualizations on remote data sets. So who here has heard about Blaze? Okay, great. You guys should all go to the Blaze talks that are happening at this conference. But essentially, part of Blaze is a Blaze web server. So I can spin up a Blaze web server, and I can load it with data sets that live on my machine and also live on SQL databases and things I have access to. And I can expose them to the world via HTTP. So what I've done is I have this data portal running, and I've spun up a Blaze server and loaded it with this data and registered that Blaze server with my data portal. And so then, anyone at my company can come and browse my list of data sets. So I happen to know that there's this iris data set that I like to use, and I can search for it, and here's the iris data set, and I get a little preview, and I also get some code that I can use to access the data set. Right, so this is nice because sometimes, like let's say you do an experiment on your computer, you do some statistical analysis and you produce some extra result data, and you want your friend to look at it. You could either try to copy it over a shared drive or something, but if it's large, that becomes cumbersome. Instead, what you can do is you can spin up a Blaze server, register it with your data portal, send this link to your colleague, and your colleague can access the data that's running on your machine via your Blaze web server. And that's what I'm going to do right now. So if I do c.keys, C is a client that's pointing at my data portal. If I do keys, I list all the data sets that I have. I can also do stuff like search, right? And that'll return, I have two data sets named iris. One is just the regular iris data set, and the other one is a filtered thing that I created. And I can actually do bokeh plots on that. So I just did this bokeh plot. Oh, that's the same one that was there. Let's do another one. All right, there we go. There you go. I'm going to remove this one. Uh-oh. And then I can, so I have these plots that I just created that's pointing to data running in this Blaze web server. I can go ahead and make a dashboard of it. Oh, this may not. Yeah, I'm not sure. Okay. Well, it seems to be okay. Yeah, I may have to reload this. Okay, so I made this dashboard, right? And can anyone give me a title? What? Foobar. All right. All right. So I made this dashboard, and then I've got this link, so I can pass this to anyone, and they can get access to this data portal. Sometimes, because of various things, it takes a little bit of time for the data to load, and that's why there's this delay here. But the data will show up there. And then, because the Blaze server is just sort of serving data, I could actually, there we go. Because the Blaze server is just serving data, I have another data set. This data is just updating every second. Oh, never mind. But I can do this. So I have this table that points to that remote data that's updating. I have to create a bokeh object out of that. So I'm setting the polling interval to be 1. That's because I know the data set updating every 1 second, so I want it to update live. All right. Yep, so my plot showed up here. And so we have it. And you can see if everything is working. When I zoom in, it should update. Yeah, there we go. Right, so you can make streaming dashboards and stuff using this tool. And this is really quite a nice approach for working with remote data because you can also do stuff. I haven't showed very much compute, but Blaze supports a lot of different compute things. Like if I go to the iris data set, so I just did a group by on a data set that's living on a different machine, right? And I'm getting the result back in my machine in my IPython session. And I can also do stuff like, so let's say frequently you're working with data, so maybe your colleague produces some results, and you look at it and you're like, okay, here are the interesting bits. I've done some filtering, this is the interesting bits. So let's do that right now. If I take this data set, if I say that the interesting bits are where the sepal length is greater than 5, right? And then I want to publish this view so that my friend can look at it. This data set is there. This is the filtered one. So I can send this to, make this bigger so you can see. I can send this to my colleague and say, this is the part that I thought was interesting, and they can use this code snippet to access the filtered data set that I just wrote, and then do subsequent analysis. No, it does not copy that data set. So what it's doing is it's storing a URI that points to the original data set, and it's storing a JSON expression graph, or a JSON expression that represents the computation that's being done on the data set. So no data is copied. At Continuum, we hate data copying. It's terrible. Never do it. And I think that's all I have. If there are questions, I'm happy to take them. We can talk about. So if you're interested in this kind of stuff, this is a product that's like new in development. Blaze and Bokeh are open source. You can go ahead and use that and do a lot of this stuff with it. But for a nice package that makes all this easier, you should look for the Anaconda Data Portal when it comes out. And if you're interested in this kind of stuff, you should drop by the Continuum booth so that we can chat about it and you can give us all your money.